I'm going to talk to you about shot noise, and I'm going to take you to the early part of the 1990s with J.J. Thomson that discovered the electrons. He worked with vacuum tubes which are containing cathodes that are being heated, allowing electrons that gain energy to get out of the cathode and move toward the anode, carrying current. And this current is composed of stochastic motion of electrons. And Schottky realized very little after this that there is also noise. And the noise that he derived from observation and derivation is 2 times the electron charge and the current that is going through the tube. In nowadays, when we go now to solid states, and we know about Pauli principle, that electron cannot sit one on top of the other, when you have a current in a one-dimensional mode, electrons move one after the other like soldiers. And their wave packets, which I represent here in this picture here, is getting shorter and shorter in time as the voltage increases, as the energy of the electron gets higher. But all of these electrons with these wave packets eventually create zero noise, because the wave packets overlap each other, and magically they create zero noise. And amazingly, this zero noise phenomena was not observed, or not, I would say, understood even until the 1990s, just a few years back. Okay? If you want now to get shot noise, and you want to measure the charge of the particle, you have to partition it. Because if you don't partition it, you have a full beam, and the full beam doesn't carry any noise, as we've seen before. But when you put some barrier, and let's look at the top barrier, which is transmission much smaller than 1. This is very much like the vacuum tube. The transmission was very much smaller than 1. You have a Poissonian distribution, and the noise is, as you see here, it's 2 EI. But when we go now to the solid, we can now change the barrier, this tunneling barrier that leads to partitioning. And when the tunnel barrier is thick enough, the probability to come is not 0, but it can be controlled to be also relatively high. And then we move from a Poissonian distribution of the current to binomial distribution. And as a result, there is another t 1 minus t in front of the current. The current itself is proportional to the transmission, and the 1 minus t is a correction. I'm just going to flash one transparency here, which I'll let you look at it later carefully to show that the noise is T1 minus T. So if you just look on the charge is electrons go through or electron doesn't go through with a probability of yes or no. It can go or, not, or cannot go. And the average probability, we call it the transmission. Since the total noise has some pluses and minuses, there is an electron, there is no electron, etc., then basically the total charge that you get in above the average is 0. We are looking at fluctuation of delta Q square, I would say. Okay? And I'm not going to go through it. It's very simple to do it. And you come up with the formula that shows you that there is T1 minus T. Okay? Transmission, 1 minus transmission. The first T tells you how much current goes through, and the 1 minus T is the binomial distribution part. Okay. So now let me give you an example why noise is so important. Suppose you have fractional charges. But let's start before we have fractional charge. Let's talk about electrons. Suppose the electrons are moving around with some space in between. I arrange it somehow that they have a space. Electron yes, 2 electrons no, etc. The conductance will be here E squared over 3h, because it's a full beam, E squared over h divided by 3. But if now I measure the noise by partitioning it, I remove an electron, you see now that the noise is E, which is okay, we understand it. But let's look now at the other possibility that we have now fractional charges. The fractional charges will carry now exactly the same conductance. Okay, so we won't know the difference. The conductance here and here are the same. If now I partition, I remove a particle, you see now that the noise will be proportional to E over 3. Even though the two conductances are the same, the measured charge is different. And that's the power of shot noise. And now, what are the regime that we are working in? First of all, if transmission is 0, then this is the formula I showed you before. But if you have only thermal, only high temperature, no current, then we have the known thermal noise, the Johnson-Nyquist thermal noise. And if I have now both of them, then you have a rather ugly formula at the bottom here, okay, that contains also the temperature, the voltage that is applied, and the electron charge and the current. And this is the formula that I'm going to use later. So first of all, we have to take the current that doesn't carry any noise, and we have to partition it. We have to have electrons going out or not going out, etc. Okay, or electrons or fractional charges. Okay? And we do it by something which is called a device which is called quantum point contact, which you are going to see again and again if you're in this field. And it creates a barrier between 2 points by applying a gate voltage. Okay? And you can change the transmission probability through this quantum point contact. And then let me give you an example. Suppose you have a line and there are 3 modes. Okay? You see here a picture with 3 modes. And when I change the gate voltage on the quantum point contact, I can have 1 mode going through, a second mode goes through, or 3 of them going through. Okay? At each plateau, you see, you have 3 plateaus here. At each plateau, there is no partitioning. 2 channels are going through, 1 channel is reflected, but there is no partitioning. There is no noise. So on each plateau, there is no noise. But if you go between plateaus and you partition the particular edge, the particular mode, I would say, that you are going to work with, there is noise. And the noise is plotted by these blue mounts at the bottom. The noise is supposed to go up because T1 minus T at the middle will be maximum, and go down at the plateau. Okay? Now, when you make this experiment, actually the experiment which we did many, many years ago, okay, the date is written down there, at a high temperature, you get something not too bad, similar to the expectation. That at the time the temperature was 1.5 Kelvin, now we are doing things at millikelvin, as you will see soon. And here is an example of a lower temperature, 57 millikelvin, quantum point contact, probability that transmission is 0.37 in this case. And then we get now this equation that you see at the bottom. We agree beautifully with this equation, an electron charge. So that's a way to measure the electron charge, and that's the way later on that we exploit to measure charge of quasi-particles. Now let's go to the quantum Hall effect. In the quantum Hall effect, which I'm not going to talk about it, here there are many, many edge modes. The bulk is insulating, and current moves around the edges. Okay? And you can have many modes around the edges. It depends. For example, here I chose an example of filling factor 5. 5 Landau level are being filled. And there are 5 edge modes on each side of the Hall bar. And if you take a quantum point contact, I'm giving an example arbitrarily that I'm allowing 3 outer modes, outer close to the edge, go through. As a matter of fact, 2, not 3. 1, the blue one, is partitioned. Part of the current goes fly back. And 2 more, totally reflected. So the totally transmitted and totally reflected don't give any noise. The partitioned one gives noise. The same story. Okay? It appears now, if we work now, as you will see in a minute, in the fractional regime. So first, another simple fact about measuring fractional quasi-particles. So let's talk about the most famous and ubiquitous, the 1/3 filling factor, which supposedly 1/3 quasi-particle, E over 3. So if you have a big fat barriers and you are going to measure the noise that you will find will be E. Okay? It will not be E over 3, it will be E because in vacuum, you see it's written there that the filling factor inside the QPC is 0. Quasi-particles cannot really survive and live in this vacuum. You have 2 different worlds now that are separated, and you cannot have 1/3 here and 2/3 left behind here. So you have now to increase the transmission probability to allow high transmission, relatively high transmission of these quasi-particles, and then you measure noise proportional to E over 3. And I'll show you a result at the end of the talk. Okay? So now I want us to show how do we do the experiment. So here's an example that you have noiseless current coming to a QPC. This can be electronic, it can be fractional, it doesn't matter. And now we are partitioning this particular green edge mode. So the noise that goes through, there is a noise that partitioned electron go through and partitioned electron go back. The sum of these two gives you back the current that you put in. But the point I want to show you is this way that we are measuring it. You see the amplifier is sitting between a contact, okay, and ground. So the amplifier, you will understand soon what the reason for the resonant circuit. But amplifier itself is a voltage amplifier. So the current fluctuation of the green line that you see there are going between this contact that the amplifier, which is this triangle connected to, goes to ground. And the amplifier feels a constant conductors, the whole conductors. If you change the quantum point contact, you close it, you open it, doesn't matter, the amplifier see a constant resistance. And this is very, very important to interpret the results. If I would change the quantum point contact and change the transmission, and the amplifier will see different resistance, it will be very complicated to find out exactly what is the current fluctuation, because I measure voltage and have to divide by resistance square. So that's the way that not only us, many of us measure noise. Okay? And now, and this is exactly what I'm trying to tell you here, the edge mode themselves are you cannot define in edge modes any really particles, because they are like plasmonic wave moving around. And the particle, the charge of the particle is determined by the bulk filling factor. When these two liquids are close to each other, quasi-particles are jumping from one to another, and their charge is the bulk, pretty much bulk filling factor. I'm simplifying it, but that's basically the idea. Now I'm going now to a fractional regime. This is, I chose to work here with a whole state with fractions which are between half and 1. And we start with a bulk filling factor of 4.9, let's say. And you can see if I take now this QPC and I slowly change the gate voltage, and I pinch it more and more and more, I can see all these plateaus now of different fractions that sit below. These are different edge modes that I'm repelling and let them go. And when I want now to measure the noise, let's say at 2/5, then I look at a step between 2/5 and 1/3. And this yellow dot there is the place I'm going to measure. On each plateau there is zero noise, but on this yellow dot, you can see there is, I wrote there, a transmission T2, which is the transmission of this little step only. Not the whole thing, the transmission of this little step, because this little step is the current that we are interested in, and the transmission from this little step. And similarly to the step below T1. Okay. So now let me just spend a few more minutes on actual measurement. What do we do in order to get this very tiny noise that we usually have? So here is just an example of carrier density and mobility of a typical two-dimensional electron gas. But the shot noise that we expect to get, rather than give you a number in amp square per hertz and 10 to the minus 29, which doesn't mean much to you, I translate it to some temperature. This particular temperature, if you put it in this Johnson-Nyquist node, will give you an idea. If you have this resistor, which is, let's say, 10 or 20 kilo ohm, and you put it at 40 millikelvin, that will be the noise that I measure. That will be the noise that I get to measure quasi-particles. Now, there is also hot noise, the Johnson's noise, the Johnson-Nyquist noise. There is also 10 to 30 millikelvin. But the temperature of the electronics, the warm electronic outside, the amplifier that I showed before, is 3.5 Kelvin. So it's 100 times bigger than the noise that I want to measure. So it overwhelms. So we have to do something about it. Okay? So the way that we do it is that we built, and not only us, homemade amplifier that we put inside the refrigerator and put it at 4 Kelvin, for example. And this amplifier now generates a much, much smaller noise. Instead of this T square that you see, 3.5 Kelvin of the warm electronics, we have now something between 100 and 200 millikelvin of the noise of the amplifier, which is few times bigger than this 40 millikelvin. And I'm going to move on and give you a bit of more details of this. This is now you see here the whole bar or the device with some current fluctuation, which I wrote as DI square. And then I go now, and I'm going to go now to the amplifier that sits up at the top at 4 Kelvin. Well, I'm measuring something at 20 millikelvin, and the distance, as you see, is about 60 centimeters in a typical refrigerator. And this will give you some capacitance. And if you now think about this capacitance is 60 picofarad, let's say. because it's a 1 puff per centimeter. And the resistance of the quantum point contact, let's say, is 100 kilo ohm. It can be also 20 kilo ohm. It doesn't matter. The RC time constant is very small, 30 kilohertz. So all the higher frequency, I should say, disappear. And I'm sitting at 30 kilohertz, where the 1/f noise, that I assume you know about it, is huge. So we have to run away from it. So how do we run away from it if we have this line that is 60 puff in capacitance? What we do, we are adding a coil. So we change the whole system to a resonant circuit. Okay? So now the resonant circuit sits in parallel with this R. This R that you see here is the quantum point contact itself, the resistance of the quantum point contact itself. Okay? I replace it by R. And then I move the frequency from 30 kilohertz. I move all the way up to something like 4 megahertz or 2 megahertz. And I just want to finish by showing you the results that we get. Okay? So in 1997, this was the first time a fractional charge had been measured by our group. It was at 50 millikelvin. And you can see here, using this ugly formula with temperature and voltage and current, you remember this long formula, we received very nice agreement with E/3. Recently, of course, we go down to very low temperature. We get pretty much similar result. But you see now here the temperature was very strong and dominated. We are using here currents which are very large, which are up to 400 picoamp to see this graph. Down there, since the temperature was very, very small, we don't have to go so high. And we are enough to go to about 10 times more current to measure the charge.